Good afternoon, everyone. Thank you for coming over and taking the time to attend my presentation. My name is Haghighi. I'm a distinguished engineer at Discover Financial Services. Today, I'm going to talk about some sort of automation with Kubernetes custom resources and operators. I'm sure many of you are familiar with that, but it's actually quite interesting that I see a lot of developers are still not taking advantage of some of the great features of Kubernetes, and that's the motivation for my talk today. Just a little disclaimer, this presentation is just for educational purposes, and all the content and the points of view expressed here are basically my own and not of my employer, Discover Financial Services. I would like to start my talk by telling you a little bit about myself and the sort of journey I've been through the world of technology. In 2007, I worked for Sun Microsystems, and Sun Microsystems, which obviously was quite ahead of its time back then in terms of innovation and so many great products that came out of Sun. And that might be actually the very reason that so many of us are still here and we get together every year. So I basically worked with a group of more than 500 academic developers around the world, and we basically build applications and promote open source software, and that motivated me a lot that I decided to do a PhD in computer science and a couple of postdocs after that. Later, I joined Intel as a research scientist, and I worked with a group of scientists across the world to implement larger scale sensor networks and also integrate machine learning into sensor systems using cloud-backed services. And later, I joined IBM as the head of developer ecosystems in the UK and later for Europe, Middle East, and Africa. So I worked for IBM for about 5 years up until May 2022. That was last year, so that was like about 10 months ago. That I decided to join Discover. So back at IBM, we worked with so many clients around the world that they wanted to migrate their applications, and they wanted to modernize their applications from a monolith into microservices and cloud-native applications. And obviously, because of Red Hat OpenShift, we promoted OpenShift as the platform that they had to run their applications in order to take advantage of that cloud-agnostic model. And now at Discover Financial Services, I look after all the infrastructure and cloud platforms and basically migrating applications into OCP and Kubernetes is still one of our top goals. So, as I said, the main focus of my talk is about automation, and that's basically about automation across multiple clouds. And by that, I mean applications that are cloud native and can be ported seamlessly across different cloud platforms. So they must be built, delivered, and operated in a way that they are not hardwired to any infrastructure. That may sound a little bit too optimistic, but that's a possibility. So developers, they can actually take advantage of so many productivity features of Kubernetes and later OCP and OpenShift Container Platform to actually make that happen and run their applications with minimal to zero rewrite and port it across into another cloud platform. So that's the purpose of this talk, and I'm going to talk about some of the automation features of Kubernetes. So in my last talk, actually, I jumped straight into automation, and I talked about custom resources, operators. And then the sort of feedback I had later was like, many attendees, they wanted to actually know a little bit about Kubernetes. I'm sure many of you are familiar with Kubernetes and microservices and cloud native, but I'm just going to give a very quick summary of what cloud native is and microservices before I jump into the automation side and how you can actually take advantage of operators and custom resources in Kubernetes. So first, we are going to start with why cloud native. I'm sure some of you might have that question. Why cloud native matters. I can tell you that a lot of enterprise, like so many companies, are moving towards cloud native and multi-cloud. We are basically going to multi-cloud, and that's why they need to adopt cloud native model, cloud native implementation and development. And then we are going to talk about the personas and decision makers and why they're actually interested in multi-cloud. A little bit about portability, which is a very important factor for having your applications on different cloud platforms running simultaneously. And then how cloud platforms actually differ, some of the public cloud platforms. We are going to talk about some of the important factors that may actually make them kind of suitable for some applications and not others. And then obviously we are going to talk about Kubernetes orchestration platform and how you can actually take advantage of Kubernetes to orchestrate your microservices. I'm going to use very basic terms here and try to explain everything very thoroughly, but then obviously the topics are going to get a little bit more advanced in the end, which obviously is about operators and custom resources. So, multi-cloud adoption. As I said, motivations for having multi-cloud applications are different. In my conversations with our clients and all the other clients that I knew back at IBM, depending on whom we were talking to, the motivations were kind of different. But then I can actually talk about the execs. So the execs are very interested in business flexibility and delighting their customers and making sure that they can add new features as quickly as possible, reduce the time to market, and just being able to adopt and basically signing new clients as quickly as possible. And the reason for that is because of data sovereignty. For instance, in Europe, some of the countries in Europe, I live in London, in the UK. So if you want to work with a client, let's say in Germany, and they've got their customers' data on a particular cloud platform or on their private cloud, if you've got your application running on Azure or AWS or some other cloud platforms, you actually have to port your application into that particular platform where customers' data reside. You can't actually work with that client unless you can actually have your application running on the same platform. So that's actually a very big motivation for people to create applications that are cloud native and can be ported from one cloud to another. Because imagine if you have your application running on AWS and then suddenly you come across a client whose customer's data is on Azure. You have to actually hire a new team with Azure skills and so many other things, and kind of going through that sort of training program, getting them up to speed, telling them about the application and working with the previous team is going to take you a long time. And I can tell you a lot of clients across EMEA in my previous role had that problem. They had to keep moving from one cloud to another. So that's actually a very big motivation for C-level to have cloud-native applications, because they don't want to rewrite the application every time a new client basically wants to adopt their application. And obviously, cost reduction in that is another reason. Sometimes by moving your workload, as I will explain later, and your application, you can actually reduce cost because cloud platforms are different, and I'm going to talk about that. But then obviously, when it comes to developers, they care about productivity features. Let's say the C-level are asking developers, you've got to create new applications that are cloud native. They don't mind, as long as they can actually be productive and being able to freely move from dev to testing to staging to production as quickly as possible and work with other developers. On the other hand, we've got operation engineers, and they care about cost efficiency, obviously, improving security, which is the number one sort of priority for them, and simplifying the operations in the organization. But then obviously, we've got the DevOps team, this new team that sits somewhere between developers and operation engineers. For the past decade or so, we've had DevOps as one of the most and the most important actually part of every organization, every IT org. And they're basically, their biggest concern is portability, being able to port the application and workload and functionalities across different cloud platforms as seamlessly as possible. Again, in the past, developers and operation engineers, they used to have a lot of kind of arguments, whose fault it is that something goes down or what happens here and there. But then DevOps are actually focusing on portability when it comes to cloud-native applications. So when we say portability, that means portability between your private cloud and public cloud, so somewhere between your firewall, and then obviously porting your application between different public cloud providers. In this case, I'm mentioning 4 of these public cloud providers. And if you can actually do that, that's actually quite nice. You can easily move your application around. So OCP, OpenShift Container Platform, is one of those platforms that actually make that happen, because OCP on Azure, AWS, IBM Cloud, and other platforms are kind of the same. So with minimal rewrite, you can actually move your application around without actually going through that rewrite. But then, as I said, there are different types of portability. Application portability is moving your application across different clouds, moving your workload when let's say there's during Christmas and you've got a digital online shop, and suddenly you've got a massive load. You want to actually be able to spread your workload. And again, using cloud native actually makes it quite possible for you. And then obviously about functionality portability or services portability, being able to offer some of the functionality of your cloud services to your clients in order for them to actually, like, enterprise B2B model, for them to actually offer it to their own clients through their own applications. And again, that's something that, for instance, you can do it through the operator hub on OpenShift container platform. I'm not going to focus too much on the functionality and functions portability, mostly on the application and workload in this presentation. So how about that question that, for instance, you may ask, what is the difference between different cloud platforms? Cloud platforms are actually very different. If you look at some of the, the catalog of cloud platforms and the sort of services they offer, they differ vastly. So for instance, comparing Amazon with Azure, with IBM Cloud, you can actually see there are a lot of differences between them. For instance, in terms of the number of their availability zones, number of services and features they have, you might be using some sort of database that is only available on one public cloud provider, or you might be using some sort of ML functionality that only Google has it. This is the sort of thing that you come across a lot when you work with different clients. They are basically using services that are kind of specific to a specific cloud provider. Also, when it comes to cost, some cloud providers are cost-friendly. The other ones are actually quite expensive. And also, they have like different billing schemas. Like some of them are monthly, like billing you monthly, daily, hourly. Again, it depends. So based on your workload, you want to make sure that you put your entire application or part of your applications on one cloud and different services on different clouds. So this way, you can actually take advantage of the great features of different cloud providers as your cloud-native application, because you can actually turn them into microservices and run them across multiple clouds. But the most important message here is down there, actually is quite small, matching the right workload to the right cloud environment. That's all about cloud-native. So you want to make sure that you're able to do that. So if you break down your applications into multiple microservices, you want to be able to run your machine learning one on one cloud platform that offers the best feature and services, and then your databases on another cloud platform, for instance, Oracle, that offers a great database feature. Again, it depends. So you want to be able to take advantage of all these features from different cloud providers. But then the most important message here is your applications they have to migrate from one cloud platform to another seamlessly. And to express it differently, based on my previous life, you want to build it once and deploy it anywhere. And that's basically what IBM Red Hat, they always have that motto. But then obviously you want to do that with zero to minimal rewrite and obviously downtime. So how's that possible? So how can you design an application that can be updated continually without downtime? Different teams, that's another important factor, can own and evolve different parts of this application on their own without depending on each other, again, based on all the agile principles. And also, your application can be easily migrated from one cloud platform to another seamlessly. And the answer to that is cloud native. What is cloud native? Cloud native basically refers to how an application is built and deployed rather than where the application resides. So that's the big statement there. So you don't want to care about where the application resides. You just want to focus on how the application is built and delivered. So, and again, as I said in the beginning of my presentation, it must be built, delivered, and operated in a way that it is not hardwired to any infrastructure. Once you design your application this way, you've got all the freedom to move your application and different services within your application across multiple clouds. So that's a very brief, kind of introduction to cloud native. I just wanted to give that just in case for those who are not familiar with cloud native and what it basically means. But then how does cloud native development make those happen, all those great features that we talked about? By relying on microservices architecture. So microservices architecture is the building blocks and the most essential ingredients of cloud native applications. And again, there's so many people who are saying maybe microservices are not really the ideal sort of model for their applications. But again, for enterprise applications with so many services, microservices basically offer a lot of advantages compared to the monolithic applications that used to be in the past. So microservices, basically a cloud-native application, consists of these discrete, reusable components known as microservices. And I'm going to give you a brief introduction into microservices and what they are. And they're basically designed to integrate into any cloud environment. And that's the most important factor here. They can easily integrate into any cloud environment because they've got all the dependencies and libraries bundled together in that microservice. So let's take a look at this diagram. We've got this digital shop, this online shop. As you can see on the left-hand side, this is a monolithic application. You've got your inventory, your billing, your catalog. Everything is bundled together as one monolithic application. And then you've got your database connected to that. On the right-hand side, we've got this microservices model. So we basically broke down all the services based on business functionalities, business capabilities. And this way, we could easily break down our monolithic applications into multiple services. And each one of these services that you can see here, like the billing and the catalog, they can actually run on different cloud platforms. They don't need to be on the same cloud platform. Based on the same reasoning that I gave you earlier, that you can actually take advantage of different cloud platforms, features, and services. So this way, your services are maintainable and testable independently, and they can also, they're loosely coupled, obviously, and they're basically organized around business capabilities. So you break down your application into multiple services based on business capabilities, and they communicate together using messages, various types of messages, obviously, as you know. And that's basically the basic of microservices and cloud native. This is what you do with your monolithic application. Let me give you a quick example based on the same sort of scenario for that online shop that we had. So we've got the catalog, filtering, inventory, recommendations, like the products that get recommended to you when you're going through a catalog on an online shop. And then you've got the billing and payment when you want to check out. I'm just giving this 5 as an example. So this is a monolithic application. We break it down into microservices. And again, the nice thing about this one is that you don't actually have to use the same programming language or the same framework or the same sort of platform. You can actually take advantage of a very diverse set of tools and services, whereas in the monolithic sort of model, that's actually not possible. It is possible, but you have to actually put so much effort into it, and it comes with a little bit of blockers when it comes to large teams and large applications. So this is going to give us a number of advantages. First of all, different parts of our applications can evolve on different timelines. So different teams don't need to rely on each other. They don't need to wait for each other to finish one part in order to start or finish another. They can easily work on their own timeline. And the other thing is, services can be deployed separately. Again, if you're going through a number of upgrades or updating your platform, or adding new features, they can easily just work on different services separately and independently, so you don't have to rely on each other. Whereas in the monolithic model, you have to actually wait and see what's happening with the others before you can actually deploy. And again, there's so many scenarios that I'm sure you've gone through that. And then you can choose your technology stack for each microservice as it best fits the purpose. So you don't have to stick to a single programming language, to a single framework. You can take advantage of different technologies. And again, when it comes to talent and kind of having the right skills in your team, this actually helps you to take advantage of a wide variety of skills in your team. That's a very important factor. If you look at the startups these days, sometimes you come across teams that they have various programming skills, and they're just basically creating the same sort of services with different programming languages and run it on different cloud platforms. And they just want to know exactly how it works and how they can actually benchmark it. So that's another example. And then, very important when it comes to cost, you can scale your individual services separately and dynamically at runtime. Before, when in the VM world, in the virtual machine world, you had to actually scale your entire virtual machine in order to kind of scale your platform when there was Christmas time, when there was your online catalog was viewed 1 million times. You had to basically scale your entire application instead of your microservices. So in that case, for instance, you just need to scale your catalog, because not many people who are going through your online shop are going to go through the checkout. So you don't actually need to scale your billing and payment. You don't have to scale your, let's say, recommendation service. You just want to make sure that you've got your catalog completely scaled and ready for people who are exploring your online shop. So that's another one. You can actually scale individual services rather than your entire application. But the most important one, if a single microservice fails, it doesn't mean that your entire application is going to fail. Not necessarily. It could actually happen, but in the monolithic application world, basically, if one service goes down, it would be really hard for developers to find out whose fault it is and who's going to address what to recover the application. And sometimes it used to take more than weeks, basically, for some applications to be back up and running. But this way, you actually know which service is down, and it's not going to cause the other services to fail necessarily. So that's a very important factor. For so many reliability purposes, companies are actually moving their applications into, they're porting their applications into the microservices model. So those are the advantages of microservices and why it matters actually to kind of go from monolithic applications into microservices. And now I want to go a little bit further. So we've broken down our application into multiple services, taking advantage of Node.js, Python, and Java, for instance, for different purposes. And then, obviously, we need to containerize each one of these microservices with all their libraries and dependencies. This way, each one of these services can easily run on any cloud platform. Let's say, if you have a Docker, for instance, container in this case, it can easily run on any cloud platform. So we've basically gone from that monolithic applications into these smaller microservices that can easily run on different cloud platforms. So this way, you've got that portability now. But obviously, each one of these containers have all the dependencies and library and can be run and implemented separately and independently. So a quick overview of monolithic applications. They were operated and designed as a single entity. And if the application failed, that means the whole application could have easily become unresponsive. And it was really hard to find exactly where the error reside, and it was really hard to also recover. And it was always the operations and developers team kind of, fighting to figure out exactly what's going on. So that was in the past world. So it's like if you, for instance, look at Titanic, it was like, one of the parts it was saying like, one of the chambers was like full of water and it was kind of, leaking into the other chambers without actually having that locking mechanism in place. So this is exactly what happens with monolithic applications because they are not separated and they can easily, failure of one can easily cause the other ones to fail. And that's why I believe that monolithic applications are destined to fail. But again, it's not a very popular sort of idea for so many developers who are working on smaller applications. But now, let's get to the Kubernetes side. So you've got all these microservices. Let's say you're dealing with a very large application and you end up with so many microservices. Then you've got that complexity of managing and operating or orchestrating all these microservices. How are you going to do that? Obviously, the de facto platform for that is Kubernetes. Kubernetes is an open source system for automating deployment, scaling, and management of your containerized applications or microservices. And again, if you start working with Kubernetes, you're going to find out that it's absolutely fascinating and fantastic. It just works out of the box, literally with zero config sometimes. You can easily just like throw your containers at Kubernetes and it will basically take care of them based on the desired state that you basically provide to Kubernetes. And that's Kubernetes, taking care of orchestrating all the microservices. So once you break down your application, then you can actually use Kubernetes to orchestrate your microservices. If you want to, going through a number of advantages that Kubernetes provide, and I'm sure you're going to be quite interested. The first one is a multi-container application must run on a multi-host environment in order to eliminate that single point of failure. So that's exactly what I said in the beginning. So you can actually have your application running on different cloud platforms, and with one control plane, you can actually reach out to all those applications, and if one fails, the other one can easily take over. And that's actually very important, multi-host environment. The other one is we need to be able to create new instances of our individual microservices containers to scale accordingly. And again, that's about scaling and replication. Next, when one or more services need to be updated, going back to the previous point that I raised, if one team is working on adding a new feature, you need to have this system in place that it can easily update it without downtime and orchestrate the platform in a way that the new feature can be added seamlessly into the mix without causing the whole application to go down. And then cluster management. So Kubernetes scales and manages our containers according to available underlying resources on the host. And when I talked about scheduling before, that's like if even one of the pods basically fails, Kubernetes is going to reinstate that and bring it back up again. So that's, again, another feature which is like the health management. And again, basically Kubernetes keeps checking our containers continually just to make sure that they're healthy. And in case of any failure, it will basically take actions to reinstate our deployment or create new instances or restore the service. And those are the 5, the top features of Kubernetes and why Kubernetes is so popular these days. So, in summary, we tell Kubernetes our desired state. We say what we expect from the platform to do with our application, and we declare that in a number of configurations. And then Kubernetes basically keeps going through this sort of it watches the state of our application, and it keeps going through this sort of reconciliation between the actual state and the desired state, and it will basically bring our application back up in case anything goes wrong or anything fails. So this basically keeps happening continually, and that's why your application is always kind of healthy and up and running with Kubernetes. But again, we are going to have some sort of automation, as I will explain later, to make it even easier for larger scale stateful applications. So that's basically what Kubernetes does. Now let's go back to our previous diagram. So we had our containers, and we want to know what would happen next that we are using Kubernetes. So I said we broke down our application into microservices, then we containerized them, and the next step is deploying each Docker container with Kubernetes. So that would basically spin up a new pod with a Docker container in there. So based on our deployment scenario, that's the desired state, that's what we ask Kubernetes to do. It can easily, each pod gets replicated. So let's say one service needs to have a higher availability. That's why it gets basically replicated into multiple replicas. So you have multiple instances of that particular service running. And for another one, you may just need just one instance. And that's how basically Kubernetes take care of that. So we first created our deployment and then scaled our deployment accordingly. Those are the replicas, that's the scaling. And the next step is to create a service. And creating a service allows our microservices, our containers, basically in this case, our pods, to communicate with each other. So this way, you basically go back to the same model that you had with your monolithic applications. So all the services are running, and now they're communicating. So it's exactly the same, but on top of Kubernetes. So you're orchestrating your microservices. And then next, we need to expose our services to the outside world, and that's basically what creating new services and expose basically does to our application. Then your applications are going to become available outside your cluster. And that's basically how you can run your, let's say, online shop. It's just an IP address and your DNS, and that's it. You've got your application accessible from outside your cluster. So this is exactly what happens with Kubernetes. If you want to know what happens, to that deployment scenario in a kind of a deeper level, firstly, we use kubectl or kubectl, kubectl, whatever you call it, that CLI tool to interact with Kubernetes cluster. I just want to make sure that it's very simple. You don't have to do much. It's just a CLI, and you've got your container, and all you need to do is you need to use that CLI to basically that lets you control Kubernetes cluster and its resources. So think of kubectl as the sort of magic keyboard that you use before basically telling Kubernetes what to do. So then going back to our deployment scenario, we use kubectl to instruct our master node to create a deployment. As you remember, in the previous scenario, we had the deployment. And then the master node processes our request through the API server and then runs a scheduler service that automates when and where those containers are deployed based on our declaration. And then each worker node includes a Docker and a software agent called kubelet that basically receives and executes order from the master node. And then kubelet spins up a new pod for every instances of our container. And then to expose our application in the end to the external network or internet, as we say, our master node creates a service to direct traffic and load balance to our pods through worker nodes, kube proxy components. So that's basically what happens under the hood, basically, in Kubernetes. And now, as I said earlier, we talked about the desired state and the actual state. And that's basically what that control loop does in Kubernetes. It's always going through that reconciliation to make sure that the actual state matches your desired state. And that's by observing, finding, or detecting the difference, and then taking actions to make sure that it goes back again to the previous state. So in this case, for this stateless application, in our YAML file, we say that we want 3 replicas for our application for the deployment. So it basically creates 3 replicas. If one of them fails, it's going to take actions just to make sure that we've got 3 instances of my app version 3 is up and running. So it will basically take actions to make sure that there are 3 instances always up and running. But here we are just dealing with one application. And then when it comes to stateful application, that's a different story. Because with the stateless application, it can easily just spin up a new pod, regardless of what was happening before, or if all of them fails, it can actually go back to the container and start a new one. With a stateful application, each one of those pods basically have their own identity and state. So it's not easy to kind of replicate that because stateful applications, they have their own persistence and they are not exactly the same. They may not have the latest sort of data. So in this case, if you have a MySQL, they're not identical because one of them could have been updated before the other one that failed. And then if you want to recover that, you have to go back and copy that from the previous pod. But again, in this case, it's not possible because you're going to lose some data. So to fully manage the lifecycle of your application, it is basically you need to have the knowledge, the domain knowledge of your application. You need to actually embed that into this for the stateful application. So the stateless, you don't need to do that. But for stateful applications, you actually need to add another layer or another controller, as we are going to talk about it, to take care of those complex applications with domain knowledge, with that business logic of your application. So a quick example here is how, for instance, MySQL works. So this is a stateful application. We've got 3 pods running MySQL. So we've got the master node. This is how basically it works. You've got the master node, and all the updates to the persistent is actually done through the master node. So I think So if you have another slave node, they can't actually write to the persistence because the persistent, the volume, it gets cloned from the first one, from the master node. And all the read and writes are going to basically go through, the writes are going to go through the master node, but the reads are going to go through their slave. Because this way, you make sure that your volumes are not inconsistent and they basically contain the same data. So this is just a quick example of what it's like to have that sort of stateful pod orchestration. So for this, you need to actually include the business logic of this particular stateful application. For this particular one is MySQL. And this way, if you look at, for instance, what's happening out there, they're putting through a number of YAML files, and it takes a very long time to go through all these YAML files, and some of them are basically, dependent on each other. So you need to actually go through them in order. And obviously, Helm is the solution that many are using these days. But again, when it comes to configuring multiple clusters or moving or migrating your application from one cluster to another, or keeping or maintaining multiple versions of your resources, it makes it very complex. And sometimes developers have to go through a very tedious process in order to make quick configurations to the cluster, to your Kubernetes cluster. And then you need to have Helm install, update, rollback, and then again, going through that all the time for different clusters, for different namespaces. So that's not obviously the right solution. But again, many people, many companies these days are actually going through that. They have the same sort of human intervention that you had with, in the previous board, basically just to make sure that all these applications are up and running. So this is against Kubernetes automation features that we stated earlier, those 5 features, is completely against that. Because if you want to have that sort of kind of tedious process and complex tasks, then there's no point of using Kubernetes. But again, it's working for many. But what is the solution? How can we actually make sure that some of these applications are running natively within our clusters and our namespaces? So just give you an idea about Helm. Basically, Helm, and the reason it's so popular is because it takes a sort of a template YAML, and it basically turns everything into value files, and then you've got this top Helm YAML file that basically connects and links to the other YAML files. And again, I'm sure many of you are familiar with that. I don't want to go through that, but it basically makes it quite complex if, let's say, one member of your team is actually leaving, or you've got someone who's going to just take care of your application over the weekend on an emergency basis, or you've got like a new a team kind of taking over to migrate the applications. They've got to go through all these YAML files. And again, I can tell you, some of the clients we had in EMEA, they had to go through 70, 80 YAML files just through the Helm charts, basically, just to make sure that the application is up and running. And it's a very, very complex process. So you don't want to do that because of all the reasons that I stated here. And again, Helm is really good for day 1 operation, day 2 operation, but it's not good for kind of continual maintenance and updating your applications if you have like a new version release every other month or so. So the solution to that is Operator. Operator is a custom controller. It's a powerful concept that enables you to automate the management for complex stateful applications on Kubernetes. So it's essentially a software program that interacts with Kubernetes API to create, configure, and manage custom resources. And just think of operators as the same sort of operator, human operator, who used to take care of all your databases and stateful applications and going through all those YAML files. But it's going to basically take care of that on its own. So custom resources, as we are going to go through that shortly, they're basically just like extensions to Kubernetes APIs that allow you to define and manage your own application-specific objects. And again, in that case, for instance, MySQL, you can actually define your own objects, and you can define your own logic for those objects, what should happen to them. So for instance, if you're talking about the deployment and the pod, those are the default resources. Let's go through that. So default resources are that pod, deployment, services, the ones that you saw. Those are the default resources within Kubernetes. So Kubernetes already knows how to take care of them, how to manage them, how to orchestrate them, because it's got the business logic for them. But then when it comes to your custom resources, you can actually define your own resources, and you can name it whatever you like. So for instance, you can define your own queue, and if you look at some of the banking services, some of the insurance companies, they've got their own resources defined within the Kubernetes cluster. And then those custom resources, as we are going to talk about it, custom resource definitions, are going to be taken care of by a number of controllers or a controller. And we are going to go through that. So let's go back to this custom resource definition, or CRD. So you can actually define your own custom resource, like the deployment, like the pod, like the service. So after you write kube control, kubectl, you can actually basically say the name of your custom resource. And that basically gives you the advantage of extending the Kubernetes functionalities. And then, obviously, the default resources can easily interact with those custom resources, and it allows you to actually open it up to other developers in your organizations on different namespaces, on different clusters. So, for instance, you could have custom resources with a different version on your development cluster and a different version on your production cluster. So this way, you can actually just maintain one operator, but for different clusters with different privileges and RBACs. Again, I don't want to go to the very advanced topics, but let's keep it this way, that you can actually define your own resources. And then the next step is you need to actually attach a controller to that. Because as I said, for default resources, Kubernetes already know how to deal with that. But then for the custom resources, you need to define your own logic, how to deal with that. Let me give you an example. So for instance, for some of the streaming services, for messaging queues and transactions going through financial services networks, they want to have their own security and compliance built in to their cluster. But again, that cluster, that logic within the development cluster is very different to the one on the production and staging and testing. So they want to have actually different sort of operators with the same sort of compliance and security running on different clusters. This actually gives you the advantage to do that and define your own logic just to make sure that everything goes through the testing and the staging before it actually hits the production cluster. So in this case, you need to have a controller with the business logic and the domain knowledge. So that way you codify all the knowledge, all the logic as like that human operator into your cluster using operators. So let's take a look at Helm versus operators again, since we've talked about operators. So Helm charts and Kubernetes operators provide an easy way for admins to deploy applications and configurations into your Kubernetes cluster. So both of them, they kind of do the same thing. But then Helm's primary focus is on day one operation of deploying Kubernetes artifact in a cluster, whereas operators are basically addressing day two management, task of stateful and complex workloads. For instance, Postgres is very complex when it comes to large applications, so you can easily take care of that. Cassandra, Spark, and again, if you're in the financial services environment, you know that those are very, very important components that you need to have your own business logic based on your own org's sort of compliance and security requirements. And then, manual configurations and prereqs and everything else, you can easily just leave it to the operator. The operator is going to run in your cluster, so you don't need to ask your developers to go through all those Helm charts to make all this configuration happen in your platform. This way, everything just runs smoothly, and you've got all the configuration exactly as you want. But there is one important factor here. When I talked about multi-cloud, if you have if you have different clusters and each one of your clusters is running on a different cloud provider, like your development, testing, staging, and production, CRDs, custom resource definitions, can be namespaced or cluster scoped. So you can actually have them within the namespace on different namespaces or on different clusters. So this way you can actually assign privileges to different team members with different sort of access to those objects. And then multiple versions of your CRD can exist at the same time. So that means if you have if you want to update your database and you want to add a new CRD, you can easily just add a new one and just put it for the development and testing developers, not everyone else who are on production and staging. So this way you're updating your operator, but just for those two clusters. The other two clusters are still working with the previous version. But once that happens, that's a very, very important factor. You can easily migrate it from one version to another. In the past, that used to take months, like 3-4 months. I remember a client that had to go through 3 months just to make that happen, migrating one to another. But this way, you could actually have multiple versions of that running at the same time in different clusters or namespaces. And then you could have hierarchical sort of relations, like parents and children. So if you basically change that parent CRD, the child is going to basically get updated based on what's happening. And if you delete that, everything else is going to get deprecated. And again, if you're talking about the small applications, that may not be a big problem, but I can tell you, big companies, big firms, these are the biggest issues. They have like meetings after meetings dealing with that simple feature, that if you get rid of the parent CRD custom resource, you want to make sure that the rest of them are going to get updated or get deprecated. Sometimes you have services running for months without actually knowing that they're running. And this way you actually can make sure that these are all happening at the same time. And then the last one is obviously RBACs, and that's role-based access control. So adding and assigning privileges to different teams, to different, even if you are basically getting external developers, you're hiring some contractors, you want to make sure that you're basically assigning the right privileges to the right people, because this way, the CRDs can easily just give specific access to some of your resources, not everything. But again, from the development perspective, they look exactly the same. So your external contractors are working exactly the same way as your developers, but your developers are on development cluster and your external contractors are on a different cluster. But they're using the same operator, the same CRD, but you've basically given it a different version and different role-based access control. So this way, you basically manage to get all those great features through operators and custom resources. I know we are kind of getting to the end of this presentation, so I have a few more slides, but that's basically about OpenShift Container Platform, and I think I've already given enough details about Kubernetes. So I'll end my presentation here. Thank you so much. I hope you've enjoyed it.